Today we are talking about continuity at a specific point. So at this point we have talked about the continuity of polynomial functions, which are continuous everywhere, and we've also talked about the continuity of a rational function that are continuous everywhere except for where the denominator is equal to 0. But we're going to extend our idea of continuity to finding if a function is continuous at a specific point. Okay, so again, just to refresh our memory, continuity means that I can draw the graph without taking my pen or my pencil off the paper. Okay, so as soon as there's a break in my graph, that means it's not continuous. So today we're going to define that more carefully because that's what we do in math, right? So we're going to look at ways that a function can fail to be continuous. Okay, so for some point C in the interval from A to B, so there's my first picture here, where it's just I've got some value x that is C and it's between A and B. That's all this is saying. There's three ways that a graph can fail to be continuous at x equals C. And this is the first one. Okay, so basically what is happening here is that f of C, right, the y value is not defined here at C. So we can say that f of C is undefined. So that's our first thing that can happen. That's one way that we can fail to be continuous, is that there's a place where my graph isn't defined. I have this, what we call a hole, right? That's a hole. I have a hole in my graph, okay? So the next picture we're going to look at here is this one. I clearly have a break, right? Here at C, my graph is coming down and then whoop, it jumps up. This is what we call a jump. Okay, and what I want to, and also I want to show up here, let's talk about this for a second, I forgot to say, that what I find here is that the limit as x approaches C of f does in fact exist, right? Because both sides of my graph are approaching the same y value, so the limit does exist. So if I put a number here, and I said that that was 2, then I would say that the limit as x approaches C would be 2, right? If it approached that y value right there. But f of C isn't defined. So in a case like this where I have this open hole, the limit as x approaches C does exist because the graph is approaching the same place on both sides. It doesn't matter if that point is filled in or not, remember? And so the limit does exist. Now for the jump, we have a different situation where the right hand and the left hand limits exist, but they're not equal. So if I put numbers on here, let's say that this is y is 2, and we'll say that maybe over here, we'll say that's 4 up there. So if I looked at these, then the right and the left hand limits agree or exist. So if I look at the limit as x approaches C of f from the left, so that means from the left, right, from this side. So here C, as I approach C from the left, my graph, right, it's approaching this y value here of 2. And if I look at the limit as x approaches C to the right, then this is to the right of C, so my graph is up here, and I've come down here, and my graph is approaching 4. So my right and left hand graphs are approaching specific numbers, they're just not approaching the same number. And so the limits exist on each side, but the overall limit does not exist. So the limit then as x approaches C of f does not exist because that's the definition of a limit to agree, is that the right and the left, this is the right, this is the left hand limits, they have to exist and they have to agree. So the overall limit here does not exist. So this is the way to show mathematically, right? So if I have a hole, then the way that we show mathematically is that we say, well, the limit exists, but f of C is undefined. If I'm trying to show a jump, then I show that the right and the left hand limits exist, they approach a specific number, they just don't match. And then my last situation I have a discontinuity picture is kind of like the first picture where I have this place that's undefined, except for actually f of C is defined, right? It's just not there. And so we have this place where essentially we have f of c existing, and we also have the limit as x approaches c of f exists. Okay, so here is f of c, right? That's that point up here. So it's up here, f of c does exist, right? That's up there. And the limit as x approaches c exists, but it's down here because the graph is approaching this open point. So this is where my limit exists, but this is where my point exists. And so the f of c exists and the limit as x approaches c exists. They're just not equal to each other. Okay, so those are the three ways that a place in a graph can be discontinuous. Okay, so at a specific point, basically f of c can fail to exist, meaning I just have an open hole. I can have a jump where the two sides are approaching a specific number, just not the same number. And then I can also have this place that looks like where f of c didn't exist, except f of c exists somewhere else. So whether that point exists or not somewhere else, it doesn't matter, the limit still exists, but the point value isn't there. Okay, so where exactly do I get these places that are discontinuous? Okay, so we are talking mostly about functions, and a lot of the functions that we're talking about are pretty continuous functions. And so where we're going to see these things occur are rational functions, right? That's like if I said r of x is the numerator, I'll call it n of x over d of x, right? That's a fractional thing that's built out of polynomials, so polynomial numerator, polynomial denominator, and I get a discontinuity in a rational function when d of x is equal to 0. It's just like my domain restrictions. That's where discontinuities occur, is where my domain has a problem, right? So I get a discontinuity wherever my domain or my problems are here. So where my denominator is equal to 0, that's where I'm going to get a discontinuity in a rational function. Okay, absolute value, they're continuous everywhere. Most of the functions that we have dealt with are continuous, so these are the ones that we're going to find where we're going to have discontinuities. Piecewise functions also we need to look at. So piecewise functions, right, it's a graph that's defined in pieces. Right, so if I have something that is like 2 for x greater than 3 or 1 for x less than or equal to 3, right, where I need to be concerned, now piecewise functions are not always discontinuous at the changeover, where here, if the d is 0, right, the denominator is 0, it's going to definitely be a discontinuity. But where I need to investigate here is this changeover. Sometimes the two pieces meet, and sometimes they don't. Now in this particular case, I've got a really basic one. Basically here for 3, here's 2, I've got a picture that looks like this. Actually, that's an open circle there, and then I've got this filled in circle here. Oh, I kind of missed one, but you get the general idea. So I have that picture. Now, I'll say, where I need to investigate is the changeover, right? Unless that one of these things is rational, and then I need to look where the denominator is 0 or something like that. But for the most part, with piecewise functions, we're looking at where is my x values changing, because as long as these two functions are continuous, they're usually built from polynomials, then this will also be continuous in those areas. It's just we need to make sure that there's not a break where these two graphs change, where the two pieces of it change. All right, so let's just look at these and discuss the continuity of these. Okay, actually there was one. Okay. So before we get actually into that, let me just I want to talk about just a couple more things here, just be very specific about what I mean. So the definition of continuity at a point, okay, so if we go back to those pictures, let me kind of show the picture, that for a function to be continuous at a point, we'll say at point C, x equals C, okay? That f of c must exist, right? If f of c doesn't exist, then I get this picture with the hole in it, okay? So that's the first condition, and I guarantee that I always ask this question on an exam, okay? So this is pretty much a guarantee that this is one of those short answer questions, okay? So there's your first thing to study for. So the next one is that the limit as x approaches c of f exists. Okay, so again, this is that case. The limit does in fact exist, and actually the limit exists down here too. So it's not enough, right? We said that f of c has to exist first of all. Okay, so that means that point has to exist. The limit also has to exist, and then this last thing is basically that the limit has to equal the functional point at there, right? Because we can draw a picture, if f of c exists, we could draw this picture here where that is where, if this is my picture, there's my c, there's a picture where that's not enough, right? Because f of c just does exist. It's not in the right point, so we need other conditions that go with it. And then also, this is also another picture where this is true as well in my picture, but it's not continuous here, right? The limit as f of x exists as x approaches c, right? Because it's approaching these same values here. So here's the point, here's the limit. They do in fact both agree, so these two aren't enough on their own. So the last final piece is that this limit has to equal the point. So basically that means that, you know, if that f of c has to be right there, and that fills in the hole. So that's the definition of continuity at a point, that the y value at c has to exist, the limit has to exist, and the limit and the point value have to be equal to each other. And then we just have a little bit of vocabulary here. This is kind of the way we talk about it. If a function is continuous at every point in the interval, in an open interval, we say that it's continuous everywhere, or everywhere continuous. And if we say if f is not continuous at a point, x equals c, then we say that f has a discontinuity at x equals c. So this is the way we talk about it. Sometimes we say it's discontinuous, or it fails to be continuous, or we can say that it's a discontinuity at x equals c. All right, so let's go back then to our example here. So we have our first, the easiest one I can come up with, where we want to talk about, we're going to talk about finding discontinuities. Okay. Actually, let me talk about one more thing real quick. Okay. Because we didn't talk about the types of discontinuities. So while we're doing the example, we might as well talk about the types of discontinuities that we're having as well. Okay. So there's different types of discontinuities. The first one is removable discontinuity. And these are the type that we like to work with the best. So a removable discontinuity basically is the type of discontinuity where the limit exists. So a removable discontinuity looks like this, okay? And we like them the most because this type of place, I get the limit that exists, and we can deal with them by finding functions that agree at all but one point. So this is like the type of, we get this hole, is what it's called. Is what we call a removable discontinuity, when I get something that looks like this. So I'm going to have a factored version here. If I have the limit as x approaches 2, and I have x minus 2 up here, and I have x minus 2 times x plus 3, right? This is one of those algebra tricks. I plug in the 2 and I get 0 over 0. So I get that indeterminate form. So then there's an algebra trick that says, oh wait, this is the same as if I did the limit as x approaches 2 of x plus 3. These two guys, or these two functions, are the same except for here at x equals 2. So these are the two functions that agree at all except for this one point. And so if this limit exists, this one down here first, then this one is the same. And so now I just plug in the 2 and I get a 5. And so this is an example. When I look at this graph, what I'm going to find here is a removable discontinuity because the limit exists here. Okay, that's the type of thing I get. All right. So ones that we have a hard time dealing with here, these are kind of ones that we can fix. Like here, like if you think about it, like all I need to do is just cover that one little hole and everything is fine, right? That one little point. So if I redefine my function instead of this as this, then my function is completely continuous and I can deal with it. These next two, the non-removable, these are the ones that really you can't just fix by redefining your function easily. And the first one is a jump discontinuity. Now we just saw a picture of a jump discontinuity. You know, a jump looks like this, like there's a break in the graph and there's a clear division here. So I can't fix that by just redefining one point. And so this is what we call a non-removable jump discontinuity. So with a jump discontinuity, we just saw that was this picture here, right? This is a jump discontinuity. And what happens with a jump is that we find that the right and the left-hand limits are there, they're just different, and so the overall limit doesn't exist. So if you're trying to justify a jump discontinuity with limits, it's you show the right, and this is the right, and the left, and they're different, and so the overall limit doesn't exist. Okay. The last one, now I haven't drawn a picture of it, but we've definitely seen it when we've looked at vertical asymptotes, but a limit that is infinite. And again, this is not fixable. So a limit that is infinite kind of looks like if this is my value c, then maybe I have this going on around c. So my limit is infinite, right? I just, when I look at the right and the left of C, they're both either going straight up. You know, it would be the same if I had one piece going up, going down. It would be an infinite discontinuity as long as one side or the other of my graph is going off to either positive or negative infinity. So this is a type of non-removable discontinuity. It's an infinite discontinuity. And so the jump and the infinite discontinuities are difficult to deal with because there's not just a place where I'm like, oh, well, I'll just redefine my function and everything will be fine, right? I can't just fill in a point somewhere and make it not infinite. So this is a type of non-removable discontinuity. Okay, so now that we know the types, we're going to find the discontinuities and call them what they are with justification. Okay, so this is a rational function. And the first thing that one of the first things we talked about was the fact that we find discontinuities in rational functions where the denominator is 0. So just like the domain restriction, x equals 1 is going to be a discontinuity. So how do we know what type of discontinuity it is? Well, the first thing we're going to do is look at the limit as x approaches 1. Once we find the discontinuity, then we look at what happens at the limit. So we're going to look at the limit as x approaches 1 of 1 over x minus 1. Now I'm going to use that technique where I plug in the value, right, that I'm going at and see what happens. Well, when I plug in the 1, I get 1 over 0. And hopefully you remember that this is an implication that x equals 1 is a vertical asymptote. Also at this point, I hope that you kind of know what this graph looks like. So that means if that's the case, then x equals 1 is a vertical asymptote, which implies what happens at vertical asymptotes? We get the infinite type of discontinuities. So this is an infinite non-removable discontinuity. All right, so that's the only place that we're going to find that, because rational functions, we talked about in the last lecture, are continuous everywhere except for where the denominator is equal to 0. That was the only place where the denominator is 0, and so that's the only discontinuity we're going to find in this particular function. So we found that at x equals 1 is a discontinuity, and it's an infinite, which is part of the non-removable classification. Okay, let's look at the next example here. Okay, so this time we have g. It's another rational function, and g is x squared plus 6x minus 7 over x squared plus 4x minus 21. And what I'm going to do with this first is I'm just going to factor everything, right? It's a good start with rational functions. So I'm going to rewrite g as, let's see, the top can be factored as what? X plus 7 times x minus 1. And the bottom can be factored, let's see, as x plus 7, x minus 3. Okay, so I can see now that I have this rational function, I know I'm going to have discontinuities where the denominator is 0. So I'm going to have discontinuities at x equals -7 and x equals 3. So we're going to look at those limits now separately. Okay, so let's first look at the limit as x approaches -7. Okay, so I'm going to rewrite my factored form here. Right, I notice right away if I plug in -7 here, well, I can see that these are going to cancel, but I'm going to get 0 over 0 because when I plug in -7 here, I get 0 times whatever this is and 0 times whatever this is. And so I'm definitely have 0 over 0, which means it's indeterminate form, which there's an algebra trick, which is very obvious at this point, right? That simplifies. So I get limit as x approaches -7 of x minus 1 over x minus 3. And now I no longer have a place where I'm going to get 0 in the denominator. I just pop in my -7. I get -7 minus 1 over -7 minus 3, which gives me -8 over -10, which is also 8 over 10 because it's positive, or 4/5. And that's my limit. So since I have a limit there, that means that this is a removable discontinuity that's a hole. When my limit exists like that, and I have that algebra trick where I can find another function that behaves just like it, except for right here, that makes it removable. It means it's a hole. Okay, so there's at x equals -7. So that's my first discontinuity. All right, so we've talked about that one. So now we need to go back and discuss when x is 3. So let's look at that limit. So we have the limit as x approaches -3. Oh, actually, it's +3. Excuse me. X plus 7 times x minus 1 all over x plus 7 times x minus 3. And this time, when I plug in the 3, okay, so I'm going to get 10 on top times 2 over 10 times 0, which I get 20 over 0, which means that x equals -3. As soon as I get this division by 0 and the top isn't 0, that implies that x equals 3 is a vertical asymptote, which implies that my limit will be infinite. And so at x equals 3, we have a non-removable infinite discontinuity. Okay, so let's look at one more type of function here. All right, so we have h, and h is a piecewise function. So rational functions, wherever the denominator is equal to 0, is a place where we get discontinuities. We also get them in piecewise functions at the changeover place. And so it may or may not be continuous here, but we're going to look. Now with piecewise functions, we need to remember that here we get the limit as x approaches c from the right of f is equal to the limit as x approaches c from the left, right? Then this is the definition that the limit as x approaches c of f exists, right? If these are both equal to the same thing. And so what we want to do here is with a piecewise function is we need to look at the limit from the left and from the right of 0, and we want to write them out separately. Okay, so again, we're trying to show continuity at a point, so we need to show those 3 things are true, that basically this limit exists, that the point exists there, and that the limit and the point are equal to each other, or the y value at that point, I guess I should say more specifically. So let's see first. Let's find so we're looking specifically at x equals 0. This is where our investigation is happening, because this is a polynomial that's continuous, this is a polynomial that's continuous. So the only problem that we could possibly have is here at the changeover. So at x equals 0, let's first investigate what is h of 0. So h of 0, right, is defined, 0 is defined up here. So I plug in 0 on top and I'm going to get it's equal to 2. Now, since I'm defined in 2 different pieces, I'm going to look at the right and the left-hand limits separately. Why am I using c? I'm not sure. So I'm going to use the limit as x approaches 0 from the left first. All right, from the left, That means for values smaller than 0, my function is defined up here. This is from the left. So x plus 2. So when I plug in x plus 2, or 0 in for x plus 2, I just get out 2, right? I could have written it like this. The limit as x approaches 0 of x plus 2 is equal to 2, because I'm just popping it in because it's continuous there. All right? So now I need to see, does the right side agree? So the limit as x approaches 0 from the right, we come back up here. This is greater than 0. That's bigger. That's from the right. So I get x squared plus 2. And it just so happens that when I plug in 0 here, I get 2 as well. And so that means that my overall limit, since my left-hand limit and my right-hand limit exist, that means that the overall limit exists. And it's 2. And then we look up here, and this is, we had h of 0 is equal to 2. So since we have the limit as x approaches 0 of h of 0 is equal to, or actually h of x, I should say, is equal to h of 0, then it's continuous. There is no discontinuity in this case at x equals 0. If any one of these did not agree and were not 2, then it would not be continuous there. So if I had the limit from the right or left, if they didn't agree and the overall limit failed to exist, or if this point here didn't match, then I would say that there's a discontinuity and I'd have to label it what type. But in this case, my limit exists from both sides, so that means the overall limit exists. And also, actually I don't know why I put the plus there, it just means as x approaches 0 from both sides. And the point also agrees there. So since everything is equal to 2, it is continuous at x equals 0. So in this case, my function is continuous everywhere, right? Because it was built from continuous polynomials, and they seem to be attached here at x equals 0, and so it's continuous everywhere. Okay. The graph will have a little bit of a bend to it, right? If you imagine what this graph looks like. So at x equals 0 on the right, or on the left-hand side, I end up with here, it's a picture that kind of looks like this. Oops, no, that's not it at all. Sorry, that's a positive slope. So it looks like this, okay? And then on this side, it looks like this. And so it's kind of got this interesting looking bend to it, and this will be filled in because this side is continuous and attached there. But it'll kind of have this little bend to it, which will be important to us later. But for right now, it's still continuous. All right, so until next time.